Here's section 3, so chapter 1, section 3, complex numbers. So we might have went over this a couple years ago and probably last year. So complex numbers is a part of the complex number system. So we have our real numbers. Those are our real numbers. And inside our real numbers, or our real number system, we have both rational and irrational. And then inside a rational, we have integers. And inside our integers, we have whole numbers. And then inside a whole, we have the natural numbers, our counting numbers. Well, complex number system is just an extension of the real. So we have our real numbers, and then we have complex numbers. And complex numbers include numbers such as I, which is square root -1, 4i, -3i. So those are just the imaginary parts, and then we can have real part 2 plus 3i, the imaginary part, or -3 plus 4i, or 2 minus 5i. So those are complex numbers, and those together, the real numbers and the complex numbers, make up our complex number system. So the question might be, well, why do we have complex numbers? Or why do we have imaginary numbers? Well, we have situations like this, square root of -16. So 4 times 4 is 16, and -4 times -4 is 16. So there's no number we can multiply by itself to get -16. So that's why the idea of this I came in, or imaginary numbers. So if we let square root -1 equal I, then I can separate square root -16 into the square root of 16 times the square root of -1. Now I can solve the square root of normal 16, which is plus or minus 4. And then square root -1, they just let it stand for a letter. Just like instead of writing all pi, which would take you forever, and you'd never stop, they came up with the symbol pi, right? Well, same thing here. Instead of writing square root -1, they came up with the symbol I. So square root -1 equals I. If you wanted to, you could name it a different letter if you wanted to, but it doesn't really matter. So I stands for square root -1. Now, if we square that, that means I would have 2 of them, right? Square root -1 times square root -1. And then when I multiply and I have the same radical and the same radicand underneath, then it's just -1, just like square root 3 times square root 3 is 3. So square root -1 times square root -1 is -1. And square root -1 is equal to I, so I squared is equal to -1. So with complex numbers, like I said, real and imaginary parts. Okay, so standard form is A plus BI, where A is the real part, and your B is the imaginary part. Okay, so we can hear some examples. I have square root -A is equal to I square root A, because we could separate it into the square root of -1 times the square root of 7. And square root of -1 is equal to I, so I have I square root 7. So once you get practice with this, basically if there's a negative underneath the square root, then we can just go ahead and take out that negative. And now we can simplify the radical. So this one would be 4i. And when we do a square root, usually we have 2 answers, right? Plus or minus 4 could equal 16 if we square them. So we put a plus or minus. It's not a big deal unless you always do a plus or minus if you're solving, like solving for x. So if you're finding or solving for x or some kind of variable, then you always usually put a plus or minus in front because you have 2 possible answers. But if you're just simplifying, it's not really a big deal. So here we can take the I out of the square root of -24, leave 24, break down 24 into 6 and 4, 2 and 2. And we're looking for pairs, right? Because it's square root. And then 2 and 3 on the 6. So here's a pair of 2s. It's only pair of 2s. So we can take 2 out with the I. And then square root 2 and 3, there is no pair there, right? Even though there's a pair of 2s here, you can only take out 2 at a time. So there's no other 2 for this one guy right here. So we multiply them back together, we get 6, and 6 goes underneath the radical. So here, when we're multiplying these operations with them, we can multiply radicals with negatives just as much as we can multiply just normal radicals that have the same type of root. Okay, so one way you can simplify this first. So you could take out the I and get square root 4, and take out the I on the square root of negative 9 and get I root 9. Now we can multiply I times I is I squared, and then square root of 4 times square root of 9, square root of 36, and that equals 6. And then I squared equals negative 1, and negative 1 times 6 would be a negative 6. Here you might be that negative 1 not too much, because if I multiply the radicands to begin with, I would get negative 4 times negative 9, which is a positive 36, and positive 36 if I square root it is 6. Here you might be careful with the plus or minus. So here you might enter it in, because this answer right here, I got a negative 6 by taking the I squared, right? But when you square root that 36, you're going to get a plus or minus. So really I would have a plus or minus. And same with that, right? So that's where you might be a little bit tricky on the plus or minus. So it doesn't hurt to always put, when you square root or you fourth root or sixth root, any even root, that you put a plus or minus. Okay, so here we can simplify square root 7 times square root 7. Whenever you have radicands that are the same and the same type of root, right, as long as it's square root, so I'm looking for pairs of 2, well, here's a pair of 2 right here, so I could take out a negative 7. And again, since it's square root, I should probably put a plus or minus here, just because I could have any of these answers here will be fine. So plus or minus 7 would probably be more technical. If you did just negative 7, it's okay for now, but really when you're solving, you need to put plus or minus. Here we can take out the i's first. So you can take out the i's first, or you could simplify by doing a negative divided by negative, since they're both under square root. Here the i's would cancel. Alright, so then I just have square root of 20 over square root of 2. I can put it under one radical, just like I can combine these two and put it under one radical. I can combine by division by putting it under radical. 20 over 2, reduce that to square root 10, and square root 10 I can't simplify from there. Okay, simplifying, we just want to break this down, break any root down till its simplest form, right? That's part of simplifying. So we can take the I out, or the negative, by putting I in front. And then we can break down 128, 64, we're looking for pairs, and 2. If I break 64 down at 8 and 8, there's a pair of 8s. So I can take out that 8, put it right by the I, not in front of the plus, but next to the I, or next to the square root. And there's a 2, only 2 in there, so he has to stay in there. 4. And now you can never divide this 2 by 4, okay, because this is a square root of 2. It's not 2, it's square root of 2, which is about approximately 1.4. So I can't cancel those, right? What I can do is I could factor out of the top right here. I could take out an 8, because I have an 8 in this term, and on this term I have an 8. So you could factor out an 8, and then so you'd be left with minus 1 plus I square root 2 all over 4. Now I can reduce this 8 and 4 to 2. So I get 2 times the quantity minus 1 plus I root 2. And then you could, if you wanted to, you could distribute that to get negative 2 plus 2I root 2. So either one of these would be the simplest form. Okay, so here we're adding or subtracting. Remember, pay attention to what's in between the parentheses, right? If nothing's in between, like this one down here, then it is multiplication. But here we have addition. So this is just like x's, right? 3i could be considered 3x. 2i can be considered 2x. So it's the same thing as you just got done with foiling, just but two binomials, right? So we're going to have a 2 times 2, or sorry, 2 terms plus another 2 terms. So all we have to do is combine like terms, right? So here, real number, add your real numbers. 2 minus 7, or 2 plus a negative 7 is a negative 5. Now I add my imaginary parts, right? Here's real number, here's imaginary. 3i plus 2i, that's a 5i. 3i plus 2i, that's 5 i's. Just like x's. 3x plus 2x is 5x, not 5x squared. I don't add exponents when I add like terms. So minus 5 plus 5i. All done there. Multiplying. 2 times 2 is 4, right? So I got to FOIL these out. I should have 4 terms. So 2 times 3 is 6. 2 times 4i is an 8i, positive 8i, so we'll put a plus in front. Negative 3i times 3 is a negative 9i. Ooh, that negative. Let me fix that. Negative 9i, and then a negative 3i times a 4i. Negative 3 times 4 is negative 12, and then I times I. Always remember, just like x times x is x squared, I times I is I squared. Now remember from our very beginning that I squared equals negative 1. So this is negative 12 times, right, this one right here is negative 12 times I squared. And I squared is negative 1, so that's negative 12 times negative 1, which is only just going to change the sign of the number in front of that. So negative 12 times negative 1 is a positive 12. So then I have 6 plus 12, which is 18. And then I have 8i minus 9i. Since they're both i's, I can take 8 minus 9. And I get negative 1, and I have the I, so negative 1i. So 18 minus 1i, or you can just do minus I. So that's foiling it out. Okay, dividing. When I'm dividing, if you want to keep the habit when we rationalize to just multiply top and bottom by the conjugate of the bottom. So remember, with complex numbers, we have a plus bi. We have a real part and an imaginary, right? Okay. So here on this I, right here, our real part would be 0, and our imaginary part would just be I, or 1i. So the conjugate, remember the conjugate's a minus bi. The first term is the same, second term is opposite, so that's a plus bi. The conjugate would be negative bi. So here the real part stays the same, 0. The imaginary part, instead of plus I, it'd be a negative I. So if you want to multiply by the conjugate, you could keep, that's just a good habit. You don't necessarily have to do it. You could just multiply by top and bottom by I, because we want to get rid of any i's on bottom. We don't want i's on bottom because they're square roots negative 1. And we don't like square roots on bottom. Okay, so we do that. We multiply, don't subtract, multiply. So that would be negative 3i over negative I squared, and I squared equals negative 1. So that's negative 3i over a negative 1. So here again we're multiplying, right? Negative times I squared is negative 1. So we can reduce that, and we get negative 3i over 1, which is just a negative 3i. Okay, this bottom one, again, the real part would be 0. The imaginary part is 5i. Okay, so like I said, 0 is the real part, and positive 5i is the imaginary. So the conjugate would be 0 minus 5i. So I don't need that 0 part because 0 minus 5i is negative 5i. So if I multiply by the conjugate, do minus 5i on top and on bottom. Again, you wouldn't have to here, but it's probably a good habit when we get into more complex ones where we have 2 terms. Instead of just 5i, we might have a 2 plus 5i. There you want to do conjugates. Okay, so now we can FOIL these again. So I have to take negative 5i times it by 3, negative 5i times 2i. So that's a negative 15i. And then 2 times negative 5 is a negative 10. And I times I, always remember, is I squared. Okay, now we can go ahead and do negative 5i times 5i is a negative 25i squared. Again, I squared basically just changes this coefficient, right? Because I squared is negative 1. Negative 1 times a negative is just going to change the sign. So we have negative 15i minus 10I squared, 10I squared, I squared over 25. Now I can fix the top too, right? Because I said I squared is negative 1, which just changes this sign. So we have negative 15I plus 10 all over 25. Now on top, if you multiplied by I to begin with on top and bottom, then you wouldn't have to reduce this, but we can reduce this because we can take out a 5 out of the top. So if we take out a 5, we're left with a negative 3I plus 2. And on bottom we have 25. So now we can cancel that 5 with that 25. So we get a finished simplified version of 3I plus 2 over 5. And that's the simplest form we can get. Okay, the last thing, power of I, this is pretty fun. So if you start out with I to the 1 power would equal I, right? I to the second power, we discussed this, is negative 1. Now I'm continually, as I increase in power, I'm just multiplying my previous answer by I, right? Because I'm increasing in i's. Well, negative 1 times I, well, that's just a negative I. I multiply by another I, that'd be negative I times I. And I times I is I squared, but I have that negative, so it's a negative I squared. So I have a negative times I squared, which I squared is negative 1. So I basically have a negative times a negative, which is a positive. So here, simplified down, I to the 1 equals I to the 2 equals, negative 1. I need more room. I to the third power equals negative I, and I to the fourth equals back to 1. And then if I multiply that by another I, when I just get back to I to the fifth is just I. So it repeats itself. Every 4 it repeats itself. So when I have problems like I to the 100th, I can use my properties of exponents that said, okay, I can raise powers to powers. When I raise powers to powers, I multiply. So I squared raised to the 50th would be 100, and I squared is negative 1. So negative 1 times itself 50 times, that's even. So I to the 100 is going to equal 1. Then I can keep that up. I to the 3. Okay, I can rewrite that as I squared to the 50th, which is 100. And then how many more i's do I have? Oops, how many more i's do I have? I have 3 more i's, right? So that'd be I squared to the 50th times I cubed. I squared to the 50th I know is 1, right? Because negative 1 times itself 50 times, an even amount is 1. And then I cubed I can see from here is negative 1, or negative I. So 1 times negative I, so I to the 103rd is negative I. And you can keep on going like that for many times as you want. All right, so go ahead and try these problems. You don't have to do all of them, but pick some that are similar, that you can do. You can do all of them if you want. We'll practice some in class.